let's talk about interpreting the magnitude spectrum. So we have gone through the trouble of creating our own Fourier transforms in 2 dimensions, and we can feed a cat image to this transform, and it produces this gray fuzzy image. And the question is, so what? Well, the point of Fourier transform is not to produce these plots, but to do things which we can do a lot more efficiently in frequency domain than in the spatial domain, as we'll see later. But before we get to that point, it's worth spending a lecture talking about what kind of information we can extract from these magnitude spectra by just visually inspecting them. So remember that each point z in the Fourier space is a complex number that has a real component a and an imaginary component b. And we can use a and b to compute the magnitude and the phase of each Fourier index. In real life, we're really interested in plotting the magnitudes, which tell us how much of each horizontal and vertical image frequency is present in the image. We usually don't plot the phase, although I've shown you how you can do this in the Colab notebook that accompanies this. So first notice that the shape of the magnitude spectrum is exactly the same as the original picture. So this is 800 by 600, this is 800 by 600. But it's very important to understand that there is not a one-to-one correspondence between a point on the original image and a point on the magnitude spectrum. That is, this point here does not represent this point here. Rather, each UV point on the spectrum, on the magnitude spectrum, corresponds to a particular UV horizontal and vertical frequency that is present in the entire image. And that brings us to the question of, well, what is an image frequency? What does it mean? Before we get to answering that question, let's talk about the symmetry of the magnitude spectrum. Whereas the origin of the image is here, in the magnitude spectrum, by convention, we shift the origin to the center, and we'll talk about this in the next lesson. So the center is the origin. This has a horizontal frequency of 0 and a vertical frequency of 0 here. So the positive horizontal frequencies are here on the right side of the image. The negative horizontal frequencies are on the left side of the image. The negative vertical frequencies are in the upper part of the image, and the positive vertical frequencies are in the lower part of the image. And for interpretation purposes, it's often sufficient to just look at one quadrant. So let's talk about what an image frequency means. So the frequency of a one-dimensional signal represents how quickly the signal fluctuates over time. In an image, frequency describes how quickly the intensity values, which is brightness or color, change as we move across space, either horizontally or vertically. A low spatial frequency means that the image is changing slowly, reflecting smooth regions with gradual transitions. For example, these white areas here have virtually no variation in the horizontal or vertical orientation. So they have a horizontal frequency and a vertical frequency that's close to 0. The sum of all the pixels with this near 0 variation appears at U0, V0 near the center. Same thing here. These black areas here have no variation, and between the black and the gray there is very little variation. So again, these very low frequency horizontal and vertical areas appear near the center. Whereas there are areas where there is a rapid change in a rapid transition. For example, along the edges, we go quickly from bright to dark, and along the details, for example, around the eyes, the whiskers, all these stripe patterns, they represent quick transitions in intensity. For example, here the horizontal stripes correspond to a rapid transition in vertical frequency, and we would see that showing up as bright spots along the vertical axis over here. So the vertical frequency is non-zero, corresponding to all the pixels that experience a rapid vertical transition. Here we have a nearly vertical edge, so we have a rapid transition in horizontal frequency. And all of the pixels where there's a rapid transition in horizontal frequency will appear along this axis over here. And then, of course, if we have both a combination of a change in vertical and horizontal frequency, they appear all around the image over here. Because we have two frequencies, one along the horizontal dimension, one along the vertical dimension, and we're trying to plot this on a 2D plot, the way we represent the magnitude at a particular UV frequency index is by the brightness of the magnitude spectrum at that point. So the brightness here represents the fact that a lot of pixels in this image have low frequencies in vertical and horizontal dimension, and each of these brightness values represents the magnitude of a frequency at that particular U and V index. So this sounds a whole lot like image gradient, the transition in intensity from one pixel to the other. So what's the difference between image frequency and image gradient? They both represent changes of intensity across space. A high gradient means that the pixel intensity value is changing rapidly, which corresponds to a high spatial frequency. Low gradient means that the pixel value changes slowly, corresponding to the low spatial frequency. And in fact, they are mathematically linked by the property that differentiation in space, that is calculating a spatial gradient, is equivalent to multiplication in the Fourier space. So then what's the difference? The big difference is this. Gradient is a local per pixel property, whereas frequency is a global whole image property. If you think back about image gradients, every single pixel on the image has a gradient vector that has a magnitude and an orientation. Then in the whole image, you have a whole bunch of gradient vectors, one per pixel, all pointing in different directions. Whereas a frequency is a global value of the entire image. A particular UV coordinate in the magnitude spectrum represents how much of a particular spatial frequency is present in the entire image. In other words, that point represents the sum of the pixel intensity of all the pixels that have that exact frequency. The advantage of considering frequency in this way is that because it's a global property, it's useful for global operations, such as filtering, compression, and denoising, where we can manipulate or emphasize a certain frequency range in the image, for example, removing high frequency noise or enhancing contrast by elevating the low frequency portions of the image.